my boots on and lace them up. A hard work, not another day to work. A hard work, that's what they say.
Actually, my first slide. So, I'm not sure what's. So what's going on there, right? Besides the fact that this is mysteriously highlighted. So do you get that? I don't know if there's any international visitors here, but but Pinocchio, I guess, is Italian. At any rate, so Pinocchio's nose grows if he tells a lie. So is he telling a lie there or not? Right? If he's telling the truth, then his nose should grow, but that would mean that he told a lie. But if that's a lie, then his nose should grow, which means he was telling the truth. Okay? So, not so clear yet what this has to do with computer science. Okay? I'm actually going to come back to this in a little bit, but I think I just wanted to start with that. So in some sense, let this go simmer in your brain. There's one part in the talk that's going to be hard. I'm going to make you think really, really hard, and this is the light version of that. Okay. So the context for the talk, the practical context, is, as stated there, hard programming problems. As Craig and particularly Christian, I just pointed out, we're asking computers to do really hard things these days. And it would be great if they were right. And the work that I do is designed to address that problem and really try to give programmers and users some feeling that, yes, this program is doing what it's supposed to do. Okay. My talk's going to be a little different from Craig and Christian. Is they gave you a lot of information, a lot of ideas, a lot of stuff going on, slides in color and so forth. But I'm going to do something really different. I'm taking a chance here. I'm just going to concentrate on one thing. Okay, because the intellectual context for this practical research that I talked about is a particular famous result of almost 100 years ago in mathematical logic. That's really the foundation for and provides the framework for quite a lot of active research these days. In fact, research that I do every day, but I'm not going to talk about my research. There aren't going to be any slides where I'm going to say this is what I do. But rather, I'm going to try to get you to understand one thing. So in that sense, I'm going to be really ambitious. But of course, when I say I'm going to be ambitious, that means that you're going to have to think really hard. But so what I'm going to do is try to give you one idea, and hopefully you'll come away 40 minutes from now understanding this one thing, at least a little bit, and maybe that's a good takeaway. We'll see how it goes. I happened to meet my graduate student this morning and told him I was coming here and told him what I was going to do. He looked at me like I was crazy, so. So maybe we can prove him wrong together. Okay. So what I will do is, there's a slide or two at the end where I will wrap up or give you the relevance of this one deep idea that really doesn't talk about, it talks about computers in the abstract, bring it around to practical relevance, give you some indication about why anybody cares about that, why Craig should continue to give me a salary every year to do this. Yeah, okay. Here it is. The definition of the word decidable. Okay, so quite simple. A problem, I'll say what a problem is decidable if there's an algorithm to solve it. So half of the talk, at least half of the talk, is going to be just poking at that definition to make sure we know what the words mean, because it's seductively, superficially clear, but there are gotchas and there are subtleties, and that's a big part of what I want to do. So to get started, when I say algorithm, there are mathematical definitions of algorithm. It doesn't matter. You won't go wrong. Anything you can do on a computer. Okay? So meaning any programming language you want, any computer you want. It turns out that's an empirical fact that all known programming languages and all computing platforms can ultimately do the same thing. Some are faster than others, of course. Some are more convenient from user perspective and so forth. But in terms of what they can actually do, they're all equivalent. So we don't need to fuss about that. It's just computer. And even when I say solve it, I want to make a couple of remarks. I'm not talking about solving things quickly or efficiently or cleverly. It's just getting the right answer. So you can use as much time in memory as you need. If you say, here, I wrote this computer program and it does this job. Oh, by the way, it takes as many years as there are elementary particles in the universe to get the answer. That's okay. For us, for this talk, that counts as solving it. Now, of course, a big area of computer science is finding algorithms that do better than that, and that's some of what I do as well. But the point I'm making is that for this talk, we're not going to care at all about efficiency. It's just a yes or no, can a computer do this or not? And I want to stress that because we're being so generous there, you might think, well, I don't really care about things that take that much time. I really care about programs that, I can get an answer in a reasonable time. But notice that if we take that very, very liberal idea of what a computer can do, if I can show you some things that a computer can't do, then it's a much stronger result. So in other words, my punchline is going to be, I'm going to point you to some things that computers can't do. And when I say can't do, I mean can't do even under this very, very liberal notion of how much time you give it. Okay, so to warm up, let's keep it simple. Let's talk about testing integers for primality. So several times in the talk, is this a pointer? It's not a pointer, right?
Yes, it is.
Top. Or maybe not. Oh, there we go. Okay. Okay. So this input question format is just a way of being very precise about what it is, what problem we're talking about. Here's another thing I meant to say. When I talk about what computers can't do, I don't mean can computers think? Can a computer decide who's going to, whether Republicans or Democrats are better? I don't mean fuzzy questions. I really mean mathematical questions. And so to make that precise, I'll very often make it very clear what the input and what the output is. Okay, so you know what a prime number is. So an instance of this problem, n might be 2, and the answer would be yes. N might be 3, the answer would be yes. These numbers don't have anything dividing them other than 1 of themselves. If n is 4, the answer is no. So all of these lines here are what we call instances of this problem. The input is n. It's either 2 or 3 or 4. And in each case, you get a yes or no answer. If the n is 999, the answer is no. If n is that big long number, it happens to be yes. It happens to be a 50 millionth prime, according to the web. So it must be true. So there's a really example of what we would call a problem to be solved. And so the question is, can a computer solve this problem? Sure. Okay. And here's the algorithm. So you just, given the input, you just start running through all the numbers, starting from 2 up to, if you think about it a little bit, you don't have to go any further than the square root of the input. But just try and just divide. And if you ever get something which successfully divides that number, then it's not prime. And if you get to the end, and you haven't found anything that divides it, you say, yes, it's prime. All right? So nothing special, nothing deep here going on at all. The crucial thing about this, from my perspective, is that notice that this isn't in any particular programming language that you know about, so I don't have to care exactly how the program works. It's clear that you could write this. They're all things that can be done by the computer. But the crucial thing is the number of times, if you give me any particular number n, the number of things you have to do is finite, and so you're guaranteed to get an answer eventually. All right. Does that make sense? Okay, so that's the sort of paradigm of a decidable problem. So let's get a little bit more complicated. So here's another problem. So the input to this problem is a polynomial. Krishna introduced polynomials for me. Thank you, Krishna. So, x cubed minus 4x squared plus 5x. And the question is, does it have a root? Meaning, is there a number that you can plug in? And by the way, when I say number, I just mean whole numbers, positive integers. Can you plug something in to get 0? Okay. So, for example, an obvious thing to do is just start trying stuff. Plug in 1 into that. You get 1 minus 4 plus 5 minus 6. You get 4. No, that doesn't work. Well, maybe 2 works. Plug 2 in, blah, blah, blah. Try it. Minus 4 doesn't work. Plug 3 in. Miraculously, it works. Okay. So here's the situation. Obviously, these different things, so I want to make it clear. In this case, the input really is just this one thing, P, and these X, 1, 2, and 3 are the sort of potential things that you might try to get the yes or no answer. And all that can be done by the computer, and eventually you get 0, so you say yes. Okay. But notice that this one's different from the earlier one. So here's the little algorithm that we just basically tried through ourselves. You try every number, 0, 1, 2, and as soon as you find something where when you plug it into the polynomial you get 0, you say, yes, I win. But see those dots there? Because this thing that I just showed you, it's an algorithm in some sense. It's a semi-decision procedure. So that's a technical term. It's not a decision procedure because there's no guarantee that you're going to ever get a no answer. Right? Suppose you try the first 50 billion numbers and all of those don't make the polynomial 0. Well, maybe the 50 billionth and one will. So at least this algorithm is this little thing that you could program by a computer, by the way. This is crucial. You can program this. It's just going to be a big, long loop if you're doing a program. It's completely computable, but it's not what we're calling an algorithm. Because even though you can trust the answer if you get a yes answer, the algorithm doesn't have any facility for saying no. And by the way, it's a semi-decision procedure for kind of obvious reasons. It's a one-sided thing. If you give me a polynomial, and if there's anything out there that ever makes it be 0, this will find it. You'll have to wait a long time. So it's a complete search procedure in that sense. But if the polynomial that is given happens to have nothing which makes it 0, and there are such polynomials, right? Then you'll never learn that in a finite amount of time by this algorithm, because there's infinitely many numbers. Okay? Okay, so here's the first, so already that's kind of a subtle point. So here's a subtle point that always trips up my students when I say this. So now this problem, the problem of give you a polynomial, ask yes or no, is there a 0, is there a root? Did we just show that that wasn't decidable? No. The second one, this one right here, yeah. Here's the problem. We pointed out this procedure, pointed out that it's not a decision procedure. So did we just show that that problem is not decidable? No, we just showed that the first stupid thing that came into your mind doesn't work. Right? To say that something is decidable, the way you prove that to somebody is to show them an algorithm that works. To show that it's not decidable, showing them one thing that doesn't work certainly isn't good enough. Okay, so that's the first important point. A problem being decidable or not is not, it's an aspect of the problem, not your own pathetic attempts to solve it. Okay. So as a matter of fact, oh, here's another example. And I think I won't drag through this example very long, but x to the 17th minus 173, x to the 9th, blah, blah, blah. And you start plugging in numbers here. No, no, no. You can go for a long time. No, 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 no. And this is sort of an example. When do you stop? Okay. So far I haven't asked you to think too hard about any mathematical things. So here's the theorem. Okay. It's a fact of life. This is called the rational root theorem. I think Gauss proved it. Is that if you give me a polynomial, and if n is going to be one of the numbers which makes it 0, then it's going to have to be that n divides that constant term. So for example, in the first one, x cubed minus 4x squared plus 5x plus minus 6, we happened to find that 3 worked, I think. But it's a theorem that even if we hadn't tried that, the only things that are possible things to make this, I wish I'd done my pausing better. I'm looking just at this first guy. The only things that could possibly make this 0 are plus or minus 1, plus or minus 2, 3, or 6. Okay? And for this one that the other one, the more complicated one, notice 37 is a prime number. Nothing divides 37 besides 1 in itself. And so if you believe this little theorem, this tells you that of all the possible numbers that could conceivably, you could plug in here, the only ones that have a chance of making it be 0 are 1 and 37. So that means if you give me this number, this big old polynomial, and you ask me, is there anything which makes it 0? In this particular case, I'm going to try 1 and see if that works. I'm going to try 37, see if that works. If neither of those work, I get to say no. So compare that to the other algorithm, which was kind of just plug in 1, plug in 2, plug in 3, blah, 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 blah. That's just mindless. Anybody can do that. Here, in this particular case, some smart mathematicians told us this cool fact about polynomials, which I'm not going to drag you through, trust me. The important thing is, now we really have an algorithm. Because this thing, it's a little bit like the other one, but instead of trying all possible numbers, 1, 2, 3, up to you get tired, here you've only got the finitely many things that divide into that constant term. And you can do an exhaustive search there. If anything works, you will find it. Okay? So that's an algorithm, and that's what we call a decision procedure. Okay, so let's just sort of recap where we got so far. So at least with polynomials, the initial statement of the problem suggested this unbounded search. Well, I'll try a bunch of things. We didn't want to call that a decision procedure. It is a semi-decision procedure, which is sometimes useful, but it's weak beer. But this cleverness, this domain-specific knowledge, enabled us to realize that there is this terminating method of a little check finitely many things, and therefore we can call the problem decidable. Okay, so the rest of the talk isn't going to be about polynomials. You don't need to care about that. But it's a really good example of the main theme of the talk, which is certain problems have computer programs which work for them. It's not necessarily the most obvious computer program which works. And for a given problem, it may mean that you need to be super smart mathematically to figure out what algorithm to use. But the crucial thing is to call something an algorithm to solve a problem, it's got to be an algorithm guaranteed to always give an answer after a finite number of steps. That's a fundamental thing. Okay. So a little bit more generally, so where we've gotten so far. A bunch of problems like primality and polynomials and other problems that we will see later on in the talk have these kind of naive search algorithms. If that naive search is finite, we call the problem decidable. That was our primality thing. So notice, again, I'll stress this. Decidable or not, that's a feature of the problem, not some particular method you're trying. So primality testing is decidable because everybody in the room realized the very first thing that comes into your mind counts as an algorithm. Other problems, though, it may be that there's this search that you're running through, but the thing that you're trying doesn't necessarily terminate. And in that case, basically, you don't know anything. Right? You haven't proved anything one way or the other. But if you're lucky enough to be clever, or maybe you look up in a book somewhere, or your next door neighbor is smarter than you and says, oh, here's a different way of approaching this problem, and it will always terminate, then you can say, my problem is decidable. What we haven't seen so far in this talk is a situation where there's a problem, there can't be any such algorithm, okay? And that's where I'm going. But again, notice, and one of the reasons I stress that polynomial thing and that funky dividing the constant term, if somebody tells you, I've got this problem in mind, and it's undecidable, there is no algorithm, think about what they're saying. They're not saying nobody knows anything here in June of 2014 which makes this problem, which gives you an algorithm. They're saying no one could ever write a computer program to solve that problem. They can't prove some crazy theorem about polynomials or some crazy theorem about primality. It's beyond the capacity of anybody ever writing an algorithm for this problem. So it seems impossible to imagine that anybody could ever truly demonstrate a problem to be undecidable. But that's where we're going, and that's where I said, I'm going to make you work hard, and maybe you'll get, because we're actually going to prove it. It fits one screen. And it's basically the Pinocchio proof. We'll see. Okay, so that's where we're at. So that was kind of dry and mathematical. So what I'm going to do is give you another example. And post-correspondence problem. So Emil Post was a logician in the 30s. I'm running out of, I don't have enough time to tell the interesting story of his life. But he came up with the following problem. And is this screen flow going to be in my way? Can I move it a little bit?
You can close it out.
I can close? Oh, that's good enough. Okay. So I stole this web page from Andrew Cumming, a guy in the UK. So here is what post-correspondence problem is. So the input is, oh man, I can't make this bigger. That's too bad. Oh, good, that works. That works too well. Okay, so the input to this problem are these, in this particular case, 3 dominoes. So think about each of these things as a domino. It's got a little string of symbols on the top and on the bottom. And you're playing a game, and you've got as many as you need of each of A, capital B, and capital C. And your goal is to play these tiles after each other so that when you read the string on the top, it ends up being the same as the string on the bottom. Okay? So in this particular case, notice that it's too bad he wrote capital ABC, but fine. So capital ABC, it makes no sense to put down B or C first because in the very first letter, they disagree. So any possible solution to this would have to start with A. So you do that, and notice where we are. Now we're in a situation where the lower tile, the upper tile has a C, and the lower tile has a blank there. So clearly, when I'm going to place some tile here, it's going to have a C on the bottom. And so the only possibility is to play tile B. Okay? So now we've got that. So now again, we've got the top has a CA and the bottom has this blank. So the only thing possible we could do is to play the B. Right? Now we've got a situation where the top is longer and it's got an A. I wish this were just a little bit bigger. Ah, there we go. Okay, awesome. If I do that, maybe that's a little better. So now I clearly want to play either A or C. Now, just to make sure you're not dozing off, which should I play now? The A tile, another A tile, or another C tile? Can you? C. Good. Everybody see that? That's clear. Good. Excellent. Play the C, and I win. Okay? Yay. Okay, so more formally, the problem in this case was this capital A, capital B pattern, set of patterns. The question is it possible to play them so that you end up with this win? In the interest of time, let me go to this one. Here I only have 2 tiles, capital A, capital B. Obviously, I've got to play tile A if I'm going to have a solution. Now I've got a situation where I need a C on the bottom. Okay, so I better play tile B. No choice. But now I need an A. I need an A here. So I have to play tile capital A, but notice it's not going to work because if I try to play that, well, first of all, the web is, oh, sorry, okay, that isn't going to work. So now where I'm at, the top has a B hanging over, and nothing in my given tiles starts with a B. So I'm stuck. Yes?
I would stop before playing since both tops are longer than both bottoms. It's never going to come out even.
Oh, awesome, awesome. Okay, great. Even better, awesome. Okay. Let's see. So before I address that, so again, this particular case, the instance of the problem was these 2 tiles. The question is it possible to play? The answer to the question is no. And we learned that the hard way, or we could have been even smarter. Okay. So this is a little bit like polynomials, right? The question I have for you now is, can you imagine looking at these different problems, and again, I'm not going to spend too much time on this guy, but you can make up a bazillion of these things. Oh, here's one more. Let's just do one more real fast. This one's fun. So in this particular problem, look at these guys. Notice we have to start with tile capital A because none of these guys agree. So we play capital A. And now kind of oddly, the rest of them are zeros and ones. It's just an artifact of the language. So if you start messing around with this, I'm not going to be too systematic about it. I just want to make it. So maybe, notice here we could imagine either doing C or D because we've got a 1 on the bottom here. So let's just try D. Oops, that doesn't work. Oh, yeah. Oh, you're sorry, there's one on the top. Yeah, okay, I'm spacing out. So you try that. Okay, now I need a 0 on the top. It could be either C or D, and I try some. You try various things. It's never going to work. Now, how do you know it's never going to work? So in the spirit of being clever about these things, notice that from having played that as my initial goal, the bottom tile has length 1 more than the top tile. Look at, and notice it's also going to be clear that I'm only going to be able to play B, C, D, or E from the rest, from time going on. B, C, D, and E, some are longer in the top, some are longer in the bottom. But notice that the difference between the top and the bottom is always 2. But we're starting with a difference in my strings of 1. And so I'm always going to be adding an even number. I'm going to be, the difference between the top and the bottom is always going to be an even number, no matter how I play B, C, D, and E. So not only are they not going to match up, I'm not even going to ever enable the top and bottom lengths to be the same. Okay, so that's a kind of a, notice that algorithm to decide whether this is solvable or not was kind of specific to that particular instance of the problem. Good, so let's come back to this problem. So the input to this problem is one of these PCP domino things. And the question is it possible to make a sequence making them equal? Just like with the polynomial problem, you can certainly just try all different possibilities. Just be kind of systematic and clever and just make sure you don't miss anything. All the different patterns of all the different ways to try the dominoes. I mean, and if there's a solution, you'll find it that way. But that isn't yet a real solution because there's no, in what I just said, there's no way to tell when to stop. So really this challenge is, can you have some super smart way to analyze any given some super smart way that will uniformly use a bunch of different clever ideas, figure out how the lengths and all the different patterns would work, that you can always figure out, you know what, there's going to be a solution to this one. No, there's not going to be a solution to that one. In other words, is there something sort of like that funky dividing the constant term polynomial thing that's a clever idea that makes you not have to do the exhaustive search? Yeah, is there some essential thing that you can, you're allowed to use like 100 different reasoning tools based on the nature of the problem, but it's got to be some one thing that works for everything. That's the crucial point. When I ask for a problem I'm not saying, here's a given PCP set of dominoes. Is there an algorithm for asking yes or no, to answering yes or no? That turns out, if you think about it, that's not a very interesting question. We're asking, is there an algorithm that is sitting and waiting, and you give it a set of dominoes, and it figures it out and says yes or no? Okay, so that's the question about whether the problem is decidable, and it's not. So we're not going to be able to do this, just the interest of time. But notice I want to make it very clear what the claim is here. The thing that Post proved is not that there doesn't happen to exist any algorithm that anybody's thought of so far to do this. Proved that the very essence, the nature of computing is such that there cannot be a computer program to solve this problem. It's like amazing to imagine that you could prove that. Okay. Right. And again, just at the risk of droning on too much about this, we're not talking about how long it's going to take. We're not talking about how much memory you need, and we're certainly not talking about the level of mathematical knowledge in 1937 when Post did this, or 2014 now. It's inherent in the problem. Okay. And so just to pause, I'm going to go further with this, but just to pause, this is the kind of result that's important, for example, in my work, because if you know that about a problem, and of course this is kind of a little toy problem, so what really matters is knowing that about problems that matter, like problems, for example, certain problems about polynomials, problems that come up in robotics, problems that come up in finance. If you know that about a problem, that there can't be any computer program to solve it, well, you can't just turn your back and say, okay, I give up. That means you now are thinking differently. You're using heuristics, you're using approximations, you're using some sort of best effort, you're changing the problem so you don't need an exact answer. So it has actual practical consequences. But first you need to know whether or not you should be searching for a real solution or whether you should be doing this kind of heuristic stuff. Okay, so that's even though this was a toy problem, it, I think, shows the nature. It's the easiest toy problem to show you which really is undecidable. Just a remark, if we go back to polynomials, so before we had this problem, I give you a polynomial, I ask you, is there a root? And those were polynomials with only one variable x in it. Well, of course, in life there's polynomials with lots of variables, x, y, z. The ones that are important in algebraic geometry and robotics and so forth are actually polynomials of several variables. X squared plus y squared plus 3 equals 0. If you ask the problem about finding roots of polynomials with several variables, so for example, if I've got 3 variables, x1, x2, x3, I'm asking for 3 whole numbers that I plug in respectively. That's undecidable. That was a very famous result in the 1950s. There can't be any algorithm that will look at an arbitrary polynomial and answer yes or no. Okay, that's super important. So what I want to do, I should have time to do this. So Alan Turing, I'm sure you know his name, basically invented computers, basically won World War II through his cryptography work. He is responsible for showing the very first undecidability result. Okay? And what I thought I would try to do is take you through the proof, because the proof fits on one slide. Okay? And I didn't have to squish the font or anything. So this is the part where maybe your eyes are going to glaze over, and if so, I apologize, it won't last very long. But I thought it's worth at least showing you how you could possibly prove something to not be decidable, because that's a big mystery, right? So it turns out that the problem in this case is a problem about programs. So that's the little foot in the door. You're going to get programs to think about themselves, and maybe we have a chance of showing that something isn't possible. So it's called the halting problem. So the input here, so the input is not polynomials or numbers or tiles. The input is a computer program. Okay. And by the way, notice a computer program is a finite object. It's just a string of symbols. So it's not really any different from a number, right? It's just a bunch of zeros and ones. So in this problem, you're given 2 things. You're given a computer program, and you're given some string x, which is going to be an input to the program C. So in other words, you're sort of anticipating, I'm going to run this program on this input. Which, by the way, isn't so crazy. I mean, that's what an operating system does in a computer anyway. I mean, the operating system in your computer is itself a program that takes other programs and runs them. So this setup isn't particularly crazy. And the question we're going to ask is, when I run this program C on this input x, will I get an answer or not, or will it run forever? Anybody who's ever done any programming has written at least some programs that run forever by accident, right? And it would be great to be able to avoid that, okay? So this is a general question. Is this input x somehow appropriate to C, or is it not? Okay? Notice, by the way, it's sort of in the spirit of the polynomial thing. One thing you could do is just take x and plug it into C. I mean, again, you've got your operating system, there's a program which knows how to run other programs. So you could certainly just take x and plug it into C and just wait to see if you get an answer. But just like that polynomial example, if the answer to this question is no, in other words, if x isn't really going to give you an answer, you'll find that out. But if you happen to be in this bad situation where C is going to run forever on X, you're not going to observe that by just doing the obvious thing. So just like with the polynomials, there's an obvious thing to try here, but it doesn't count as an algorithm. And so really the question is there something clever? Is there something analogous to the dividing the constant term kind of thing? Some way to do some really cool program analysis, figure out loops and data flow, all this kind of stuff. Can you do something which will anticipate, oh, you know what? Yeah, that's going to run forever because this loop is never going to terminate. Could you do that? Okay, thanks. Good. So Turing showed no. So this is called the undecidability of the halting problem. The result is it's beyond the capacity of computers. Well, let's just say it's beyond the capacity of a program that you might write that will, it's beyond their capacity to anticipate and predict behavior of other programs. And notice, we're certainly not saying that you can't do this for any particular C. If you give me some particular really, really simple C, well, then I can look at it and say, oh, yeah, it's not going to run forever. Or if you give me some particularly stupid C, I can look at it and say, oh, yeah, that's going to run forever. The thing that you can't do is have one decision procedure, one sort of analysis thing, which is guaranteed to work for all C. Okay, so let's prove it. Proof by contradiction. We assume that there is such a thing and we're going to get a contradiction. So for now, let's just suppose that there's a program that's called halt test, and it does exactly this. It takes, so notice that this C and X, this is the input to the problem, and halt test is the algorithm looking at this input. And it's going to say yes or no. I wrote 1, 0. I probably should have written yes or no. It's going to say 1 if C would halt on X, and it says 0 if C would loop on X. I should have put the subjunctive in there, but because we're not saying that halt test runs C on X, halt test is trying to anticipate or predict what C is going to do. Okay? Good. So we're assuming we've got that, and the punchline is going to be a contradiction. Well, look, if you have that, then I could write this program. So what trouble does is it takes only one input, so that's a difference. It just takes C. And what it does is it calls this halt test thing when the X is the same as C. So if you run halt test and you ask, is this program going to halt on itself? And again, just by the way, that's not so crazy either. Running a program on itself isn't, I mean, a compiler can bootstrap itself, a spell checker could spell check itself. I mean, programs are just files and they just take files as input, and there's nothing really fancy going on here. So what trouble does, though, is it calls halt test, and notice it reverses the answers. So in other words, if C halts on C, that means that this halt test guy is going to say a 1. But trouble just says, oh, you know what? This thing gave me a 1. I'm just going to go into an infinite loop. So what halt test is really, what trouble is really doing is going to call halt test, intercept the answer, and if halt test says 1, it just makes itself go into an infinite loop. On the other hand, if halt test says 0, then trouble just leaves that alone. All right. So this is a crazy program, yes, but the thing you have to believe is that if it were possible to write halt test, then writing trouble C is a complete piece of cake. Okay. So of course, what happens when you run trouble on itself? Just plug in the definition. So here, this trouble is playing the role of that C. And if you just write this down where C is replaced by the word trouble, you see that trouble is supposed to go into an infinite loop if trouble halts on itself. On the other hand, it's supposed to give 0 if it goes into an infinite loop.
Pinocchio's nose.
Pinocchio's nose, exactly right. But one difference is it's kind of easy to explain away or not care too much about these kinds of Pinocchio's nose or the this sentence is false kinds of things. You think philosophically, oh yeah, this is just a mixing of language and meta-language, or it's a philosophical problem, and that's fine. But this is code. I mean, this is real computer code. There's no fuzziness here. Okay. Okay, so I need to wrap up. So once we've proved that halting problem is undecidable, and that also, by the way, is kind of a bizarre problem. Who cares about programs halting on themselves? That's kind of an artificial problem. But the nature of things is that once you have that foot in the door, once you know that some problem is undecidable, that's the way you get other problems to be undecidable. In fact, the PCP in particular. Because what you do is you say, aha, I've got my problem. Now I'm going to show you how to translate this problem into the halting problem. Actually, sorry, that was dumb. I'm going to show you how to translate halting problem into my problem. And if I could solve my problem, that means I could have solved the halting problem. Oh, but I already learned I couldn't solve the halting problem. So there's a huge variety of undecidable things. And basically all of them come back down to this thing we just did. What you do is you basically show that this problem is complicated enough that you could code up computers halting. All right, so I need to stop before questions. There's a slide here about Girdles' incompleteness theorem, which I would love to talk to somebody about in the break or something. This is actually connected to this famous result about true things that aren't provable, but I can't have time to talk about it. And relevance to computing practice. Maybe I already gave you this slide. In other words, you have to deal with hard problems, even if they're undecidable. And so a big part of computer science research is dealing with undecidability, accepting the fact that here's certain problems. You just can't write a program which is guaranteed to give you the right answer all the time. So you make a best effort. Do an approximation, you do some heuristics, you just accept it. But it's really good that everybody knows that the problem is undecidable. Therefore, you write a paper, you don't say, you know, I wasn't smart enough to figure out this problem, so here's a best effort. That's no good. But you say, this problem is undecidable, and here's my best effort. That's much cooler. Okay. So just to summarize what I've told you, many problems can't be solved by computer. Okay. And when I say that, I don't mean that they take too long, or they're ill-specified problems, or that we just as a human race aren't smart enough yet to solve them. No, in fact, what we really mean is that these problems are inherently and of their very nature not possible to be captured by finite computation. And again, just to stress this fact that when we talk about a problem being undecidable, you're not making a remark about somebody's algorithm or the state of knowledge. It's just something about the problem. So that's really a deep and interesting thing to think about, that there's something about the problem that resists computing in an absolute sense. So I'll stop there. Thank you. Secret hand signals.
I'm sorry, Karen.
5 questions and 10 for the moderator.
Oh, okay. So 15 minutes? 15 minutes.
So I had a question. You're talking about real-world problems. Some of them are formally undecidable. Others are just like NP hard. As a practical matter, there's not enough time to say.
Right.
Does that make much difference in then what you then decide to do in terms of heuristics and
yeah.
so on? Do you really care which reason you have to approximate?
That's a really good question. So he's pointing out the fact that there are a lot of problems which are known to be decidable in the sense that I just described it, but you can also prove, almost, that you're not, it's fuzziness, that you, even though there's a dumb algorithm which always terminates, it won't terminate quickly. And so they're sort of outside the reach of accuracy. And the question is, a really good question is, here you've got two problems which are in some sense you can't do, and you're going to respond to those by heuristics or approximations. Are the responses different in those two situations? Slightly different. In each case, you're going to look for an approximation with the NP hard things, the things that are too complex, even though they're really decidable. There's been a lot of research in understanding the structure of what makes those hard, and there's this idea of a phase distinction, like with different problems. A lot of times you can say, boom, 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 these are hard, and then all of a sudden there's this one place where there's a spike that makes them hard, and then you can try to get yourself on the other side of that spike. So there are technical responses, really kind of technical things. In a broad sense, the answer to your question is no. You kind of, in both cases, just make a best effort. cool question.
The other two speakers mentioned being interested in conference proceedings. What
Oh.
resources are useful to you in your field?
Yeah, but it's the same. I mean, the stuff in this field is not so different. There are the flagship conferences, which I can give you the names of, and journals are the sort of either the salon de refusé, if you don't get to the good conferences, or sometimes you'll take papers, like a couple of papers from conferences and stitch them together and make up a big picture. It's not so different than what they said. Sorry. Yeah.
Slightly related question. Is lecture notes in computer science, that series of
Mhm.
conference proceedings, in any way a hallmark of being a flagship or a good conference?
No.
Was it ever? Has it ever been?
No, lecture notes, I'll see if you guys agree. Lecture notes in computer science, basically, it's a huge grab bag of things. Sometimes it's proceedings of really good conferences. Sometimes it's the records of little meetings where like 3 guys got together. So
I ask because it shows up with high impact factors roughly 10 years ago, the last time I did some research. And that's why I wanted to make sure that I asked the question of you guys.
I would say the high impact is due to the fact that they're just everywhere. Like 27 come out every 60 seconds, and so yeah, it's hard for us to keep track.
Right.
You have a question?
So this might be a really dumb question, but with quantum computing and the like non-yes/no possibility, does that
Right.
impact this at all?
No, not a dumb question. Well, it's a question I don't care for very much because I don't know. It's an area that I don't know very much about. So every once in a while, an undergraduate will come up to me after and say, "How about quantum computing?" I'm not expert enough. I mean, so I don't have an independent opinion. The received view in the community is that probably not. But I don't have a really good answer. Okay, yeah.
My memory might be faulty on this, but I think I recall that
I don't think that, no, it hasn't been proven. I mean, every once in a while people will say that, but I'm pretty sure I would have heard about it if it happened, yeah. So now that's still a big open question. Yeah. If you don't know what P equals NP is, invite me back next year and I'll give a talk about that. It's hard to capture in a quick second. This may be the segue into